Hi, I'm Saida Hushmandi and I'm presenting data-efficient multimodal human action recognition for proactive human-robot collaborative assembly, a cross-domain future learning approach.
In this paper, the proactive collaboration between human and robot in car part assembly is studied. To understand the context and relevance better, we should get back to Industry 4 era, when with smart technologies like AI and Internet of Things, we focused on industrial automation and improving personalization. We didn't stop there. We got to Industry 5 when, as EU has formulated, the concentration was on human centricity and sustainability. The human robot collaboration, or HRC, improved and advanced from a basic coexistence to proactive HRC. And proactive HRC is characterized by mutual understanding and empathy between human and robot, especially from the robot side. And for that, a high level of cognition for the robot is required. And the mutual empathy is mainly from the robot side. For example, the robot is required to bring something for the human operator, but the operator is busy doing something else. So the robot should be able to understand the intention and pause there and wait for the operator.
The bottleneck in HRC, human activity recognition or HAR methods, come with their own limitations. They are either sensor-based or vision-based, each of which has their own pros and cons. For example, sensor-based methods, although they look very promising in terms of accuracy, they have these problems that they have to be connected to the and attached to the operator, so they can be very limiting for them, especially in the industrial environment. In some cases, they can cause harm. The other problem is that they are not that context aware. So, for example, we cannot understand when the operator is picking something, we cannot understand if they are picking a screw or a screwdriver. Vision-based methods, um, they don't have these problems. They are context aware. Uh, Features can be extracted, meaningful features, and they can be occlusion proof too, depending on the method. But they have this problem that um, the data collection is very labor intensive. The operator has to repeat the activity several times, or a group of operators have to do that. And the data is not reusable. And since we usually use neural network methods, we need a lot of data. So there is some cross-domain solutions, which means that we train the model on public data, which is usually on more general activities. And then we test the data on we test the model on another data set. It causes domain shift, and or this domain shift can cause many complications. And the goal should be a fast learning model from very limited data. Writers of this paper have reviewed related works and papers that brought a lot to this field. If you want to categorize them, it can be as follows: general vision-based hair, vision-based hair in HRCA. And HRCA is human-robot collaboration in assembly. And few shot hair. Under general vision-based hair, we can talk about two-stream inflated 3D CNN or I3D, where uh, writers were trying to extract features from RGB videos. Human body skeleton was also uh, an important revolution, and it brought uh, generalization to the field and made the generalization better. Fusion-based and co-learning methods were of importance as well because we could use different modalities and techniques, vision-based techniques or method. Vision-based hair in HRCA, context-aware deep CNN. One of the early papers was discussing methods to extract features from the environment, from RGB videos, to get a better context-aware approach. There was another two-stream CNN in which spatial stream was for each individual frame, and the temporal frame was for all the frames. Few shot hair. In this category, we have metric-based meta learning, where the correspondence of different data sets were studied, and hybrid relation guided set matching. In this case, also was trying to study the misalignment between data sets and improving the resiliency in these cases. But how are the writers of the paper going to overcome the challenges? The proposed solution and method consists of three major steps. Hierarchical multimodal data fusion. They collected the data through three different methods or channels: human body skeleton data, RGB videos, and depth maps. Then they joined them together using a hierarchical data fusion method, and it helped them to to extract features, multimodal features that was robust to many problems like occlusion, and it was also context aware. The next step was called temporal cross transformer. In this step, they were basically trying to find the correspondence between the support set and the query set. The support set is the set that is used to train the model, and the query set is for testing the model. Um, the last step is a lightweight domain adapter. It's basically a method to make sure that the model is able to work even with limited data, and it should be integrated into the first two steps. The writers also did a lot of experiments in the HRCA setup, and the results were amazing because their model with very few and limited data could compete with um, similar works but with larger data sets. It was especially working very well, and the performance was very good um, in cases where data was very limited, like 1 to 5 videos per action. And there were cases where the performance of this model with just one video was as good as the performances of other models with um, as many videos as 10.
Experimental setup. As we mentioned earlier, in this paper, industrial HRCA is studied, and to be more precise, the task was car engine cylinder head assembly. 5 operators did 50 repetitions, 250 videos in total, 3 camera views were used, meaning that from that 50 repetitions for each operator, 30 of them were from front view, 10 from back, and 10 from sides. The workbench was blocking the operator in some cases, meaning that the occlusion was also taken into account. As we can see in the image, it all starts from the operator checking the environment and assessing if it is ready to start. It is followed by the robot picking up the injector, fuel injector, and delivering it to the operator. The operator does 8 actions, and 5 of them are marked with stars. These steps are very important for recognition by the robot. Evaluation of the methods. For training and testing the method, method training the model, public data sets were used. However, the public data sets usually have this problem that they are on daily activities which are not close to industrial setup. However, the writers try to work with those data sets which are closer or close enough. And for the meta testing, HRCA data was used. For the evaluation, mostly few shots were used, 5-way, 5 shots, 5-way, 1 shots. But it was also considered to use bigger data sets so that the method could be really compared to other methods or existing methods. Ablation was also used. So they started with skeleton-based cross transformer, and other components were added one by one.
The writers report a very high performance for their model, especially for a few shot cases, and the performance can be as high as 91.74% for 5-way 5 shot, and and the fine tuning time can be as short as 37 seconds roughly, which is by far better than other models. In spite of all the satisfying results, there are still noticeable issues. One of them is extensive meta training. Since the writers are using multiple public data sets, it takes them a notable amount of time and resources to retrain the model. The other problem is dumbing gap, since uh, the difference between the uh, public data sets and needed data is huge. They still need to record hundreds of videos. The experiment setup is not that realistic as well, and it's so isolated. However, there might be some remedies and solutions. One of them can be adding sensor-based modalities, although we discussed that they have their own problems, like limitations for the operator. Um, a, a limited number of sensors can improve the performance and can be the solution.